Thank you. Thank you for the introduction. And I thank, first of all, the organizers for giving me this opportunity to speak in this conference. And I'm very happy to talk about, actually, this is my thesis work. So let me start. So first we fix some notations. E is going to be a large number field. OE, the ring of integers of E. L is going to be a fixed prime ideal in OE, and little l, which is L intersect with the positive integers, is a rational prime, and we are going to always assume L is greater than or equal to 5. All right. Now, EL is the L-adic completion of E. OL is the ring of integers of EL, and I'm going to fix an embedding. So this is the completion of the algebraic closure of EL inside C. So if I have a element in EL, I will think of it as an element of complex numbers via this via this embedding, and it will be suppressed throughout. N and N prime are square free natural numbers. These are going to be the levels of the cusp forms. K and K prime are integers. This is going to be the weight. These are positive integers. They are strictly greater than 2. And Skn will mean Sk gamma 1. So with this, I'm ready to state theorem. My advisor. So let H be a cusp form of weight K and level N, and H prime and H double prime are cusp forms of weight level N prime, with K prime K is at least 2, such that H prime, H prime, H double prime are all new forms in the respective spaces. So by new form, I mean it's a Hecke eigenform of level exactly n and normalized. So the first Fourier coefficients, each of them is 1. And from Hecke theory, we know that the Fourier coefficients of all these forms are going to be algebraic integers. And the large here means E will be assumed to be large so that it contains the Fourier coefficients of each of these forms. And for some n, so n is fixed. Suppose we have that the Fourier coefficients of H prime and H double prime are congruent modulo L to the power n for all primes P, and the Galois representation attached to H prime and so H double prime as well, modulo L are irreducible. So this was what was in Professor Tillowin's talk, that we assume that they're irreducible, or in other words, non-Eisenstein. And going to assume now L not in S k prime union S n prime union S C infinity. Then for integers between these two numbers, I will explain in a moment what are they. The successive ratios of the Rankine-Selberg function, or the special values of the successive ratios, are congruent modulo L to the power n. Okay, I will remark on what is the set S k prime. It's all primes that P is strictly is not equal to k prime, and S n prime all primes which divides 6n prime. Again, this was present in Professor Tillowin's lecture, that these are some kind of exceptional set. These are in congruences, they usually call this small primes. So the idea of this set, it's actually a finite union of finite primes, and the point is to reduce this set as small as possible. So I've described what is S k prime and n prime. Over the talk, I will explain what is this SI and S infinity. You might have guessed from the notation that S infinity, it has to do something with infinite place. So I'll explain when I get there. So, okay, what is the motivation to look into this problem? So this actually came through a computation. So I'll explain one of the result towards that. So I'm considering two new forms, H prime and H double prime, from weight 24 level 1 cusp forms. This is of dimension 2. This is dimension 2. Yeah, dimension is 2. And I pick the Ramanujan, I pick the Ramanujan delta and it is the fact that the Fourier coefficients are congruent. Sorry, first the Fourier coefficients are actually in this number field. So this is a quadratic extension of Q, and this 144169 is actually a prime number, and that prime is ramified in this number field, and there is a unique prime ideal lying above 144169. We call that A 144169. This is another fact that the Fourier coefficients are congruent modulo L144169. It's a nice fact to prove actually. So this also confirms the heuristic which was mentioned by Professor Tillowin in yesterday's lecture, that compared to the weights here, which is 24 and 12, the congruence prime, this prime is actually very large. 144169. So making these assumptions, we are not losing much of the information. Then for h prime, sorry, h prime and h double prime as above meaning as here, and for m between 18 and 22, we have that the successive ratios for the pair h comma h prime, and for the pair are congruent modulo L144 and 69. So let me explain how we got this. So there is a closely associated Dirichlet series. By the way, I forgot to mention one thing. This notation is a little different from what Professor Tiloin had used yesterday. That L is going to denote the completed Rankine-Selberg L function for us. Okay, and here there is a closely associated Dirichlet series to this, and it's a theorem of Shimura that he has interpreted this L value of the Dirichlet series in terms of a Peterson inner product, and it is a theorem of Hida that how to compute something called the holomorphic projection. Based on that, we have devised an algorithm to calculate the algebraic part of the numerator and the algebraic part of the denominator, meaning there will be some periods which you have to divide by. When we take the successive ratios, the periods get cancelled, and we have computed these ratios and then checked this thing, and so we get this result. And there were other instances as well of such congruence happening, and which was what led us to look into a theorem of that kind. And the rest of the talk I will give an overview of the idea of the proof as to how to prove this theorem. And here this this integer is so this L function, the line of symmetry is this quantity inside the bracket. So this is little bit to the left of the line of symmetry and all the way to the right of the line of symmetry, and we will be concerned with that set as of now, and I will comment towards the end what happens to the left of the line of symmetry. No, we don't have examples, but the proof is works through for and here actually there is no super congruence here. It is one only. So in all the examples we have one actually. So now we are basically the idea of the proof will involve the work of Harder and Raghuram. So towards that we will be concerned with cohomology of locally symmetric spaces, and because that is what will give us rational and integral structures importantly for the for our proof. So I will just recall some of the notations which was already established by Raghuram in his talk. So T is the diagonal torus, and we have said 2, and then K infinity, I'll put a 2 here. He hadn't used, I don't remember if he had used a 2 because we will be looking at other group also. So this is the this is compact, the maximum compact, little bit thickened, and we are always going to fix a level structure. So this is going to be in Zarat, and this is the notation. This is slightly different from what here used. This is going to be GL2A mod GL2Q mod and this notation also was already established. This is the space of all homogeneous is homogeneous of degree k minus 2, and mu I'm thinking of as a weight here. Mu is a dominant integral weight, and that has this very nice realization. And for any ring R, commutative ring with 1, I'm going to, this is going to be defined by base change of the module to R, and the cohomology groups under consideration will be H1 shriek of this locally symmetric space, with coefficients here, and here A can be any one of these rings, right? And so there is a Hecka action. There is a, yeah, O2 mod SO2 action and a Hecka action. And both of them commute. So now the O2 mod SO2 is Z mod 2, and each isotopic component will be denoted by this epsilon prime. And for the isotopic component of the Hecka action, we'll be using this notation. So we are thinking of sigma f as automorphic form, and via the isomorphism that is actually defined over C only, not over the other fields, but we can still think of the isotopic component system of, we can think of it as system of Hecka eigenvalues. So we collect, so the Hecka isotopic components will be denoted in this notation, co-shriek GL2 for the group GL2 for the weight mu and for the level n, and we shall assume that say if I base change the sigma f to at the translator level, this is isomorphic to actually pi h twisted by k by 2 minus 1. So I'll explain what is this. This is the automorphic form, which is a map from GL to A to C, which is obtained from the cusp form H, and pi h is the automorphic representation generated by it, and we twist it to the power of determinant, and then sigma prime f is going to be isomorphic to pi h prime rho twisted by k prime by 2 minus 1, and sigma double prime, or maybe the finite part I should write, because I'm only considering the finite place here. So maybe I'll put the f. This is isomorphic to pi h double prime twisted by k prime by 2 minus 1, the finite part. So I'll explain what is this notation rho here. So if I start with a cusp form h prime, then I apply complex conjugation throughout, then it still remains a new form of the same level in prime, and this is the automorphic form associated to that, and this is automorphic representation generated by it. This is just done so that there is not any dual present in the theorem. So because yesterday in Raghuram's talk he had mentioned Langlands calculation where the ratios which appear involved a dual. So a sigma cross sigma prime dual. So that is the reason we are doing this. Okay. Now here is a tiny section to fix an integral structure on the Tate twist. Okay, the Tate twist, the level of rational cohomology, it makes complete sense. But for integral, we will fix one level structure. So I'll make this assumption: n is greater than 3. I'll come to it in a moment. I'll explain why I make this assumption. And this is going to be my notation. Mu m is going to be mu twisted by m times of the determinant. And so we have this is a fact that this locally symmetric space is isomorphic to the upper of plane modulo gamma 1 n. This is a slightly different notation from Raghuram in the first lecture. This is the complex upper of space, and we have a series of isomorphisms. Um, so S1, 2, n. Or maybe I'll just write OE for now. Upper of modulo gamma 1 n tilde mu OE, and this is isomorphic to H1 shriek gamma 1 n mu OE. This is without the shriek, this is the usual group cohomology, but the shriek will denote the parabolic cohomology groups, which was initially defined by Shimura. And by the way, I forgot to mention here the parabolic and cuspidal both are the same because of the assumption k is at least k is greater than 2. So we have this inner cohomology, which is also the parabolic or cuspidal cohomology. And now, as you can see in the definition of this, when writing it out, since gamma 1n is actually a subgroup of SL to Z, there is no determinant involved. So what we are going to do is fix the group at the last, gamma 1n mu OE, to be the lattice in M. Now I am considering Tate twist as well for all M. For all M an integer. So I'll fix this to be the lattice in everything, and from this isomorphism, it is clear that these two are isomorphic as OE modules. The Tate twist will appear when we consider the Hecke action. All right. Now I will come to some classical results. So now what we are going to do is we are going to pick cohomology classes appropriately such that they are congruent modulo L to the power n. And for that I will recall some classic results. First is Gorenstein property of Hecke algebras. So here A can be any one of these rings, and Skn comma n is of the cusp forms whose 2 expansion, if I consider, then which is in Skn, whose Fourier coefficients lie in A. This we had seen in first lecture of Rossetti-Loin, and H n comma A is going to be sub of the endomorphism algebra of A. So this is the Hecke algebra generated by all the operators, and yeah, it's a commutative ring with 1, and this acts on these cohomology groups as well. This algebra acts on these cohomology groups as well. Then there is a perfect pairing between the Hecke algebra and the cusp forms to A, which sends an operator T and a cusp form F to the first Fourier coefficient of the cusp form where we apply the operator T. Okay, I'm sorry, now I'm going to write on the other side of the board. But I will need something. So all I have said there is we have a perfect pairing. And we are going to consider this algebra morphism TP going to the complex conjugate of the pth Fourier coefficient of H prime, and then theta prime n going to denote reducing theta prime modulo L to the power n, then kernel of theta prime 1 is a maximal ideal of the Hecke algebra. Then theorem that if assume L is coprime to 6n and I have one more assumption, L is greater than k prime, and the Galois representation attached to theta prime, meaning theta prime, so given a ring homomorphism, we can think of it as a cusp form via that perfect pairing, and we have rho theta prime, which is a Galois representation attached to that cusp form. Mod L is irreducible, then H k prime n prime OL localized at L is Gorenstein. All right. So this was also present in Rossetti-Loin's talk yesterday, and even though he said there were like cases where some freeness hypothesis won't hold, here will be sort of a nice situation. So this being Gorenstein and the perfect pairing gives us this fact that I take the inner cohomology group and localize it at L. It's a free L module. So if we are in a very nice situation here, and an upshot of this fact, and no, I've taken epsilon prime. Yeah, epsilon prime. Yeah, free of rank 1. And so from this we get a theorem. So first, this is a starting point. We are picking two cohomology classes. So there is I'm going to denote by v prime h prime not v prime mu h prime rho. Okay, mu prime h double prime rho in uh, this space. Okay, such that they are both not 0, or maybe first I'll write out this thing. So they both are congruent modulo L to the power n, but the point being they are not 0 modulo L to the power n. This is very crucial for us. And similarly, we have vectors v epsilon prime mu prime now t twisted by -2 h prime rho is congruent to the epsilon prime mu prime t twisted by -2 prime rho mod L to the power n. But they are not 0 modulo L to the power n. But these two are just as elements. These two are the same actually. These two are the same actually. Only thing is, when we consider Eka action, there will be a Tate twist which will be appearing because the choice of the lattice we had fixed. And I'll just mention what I mean by congruent modulo L to the power n, because these are not scalars. So this is just a simple formalism. Suppose we have vector space over EL, and L is lattice, OL lattice inside V. Then if I say two vectors V prime are congruent modulo mod L to the power n, by definition this is V prime minus V double prime. Yes, sir. L to the power n L. Okay, so that is thing fancy here. So this is the usual definition in the presence of a lattice. All right. Now, yesterday Raghuram had mentioned the Hecke operator. The standard intertwining operator is interpreted at the level of cohomology. So it is going to be an map between two induced spaces, and the inducing data is coming from the Levy subgroups. So towards that, I'll be defining locally symmetric spaces. Yeah, sure. So towards that, I will set up some more notation. So T4 is the diagonal torus, and hereafter lambda, if I write this, it is going to be a dominant integral weight for this torus, and P is a 2-2 parabolic subgroup, and UP is the unipotent radical. And kappa P is going to denote this projection P mod UP, which is the Levy quotient, and this is isomorphic to GL2 cross GL2 over Q, and SMP n cross n prime is going to be this locally symmetric space MPA quotient order by MPQ modulo K infinity MP naught. There is a maximal compact for this R points of this reductive group MP, and then the level structure. Right. So from these two classes, then we. Oh yes, yes. Thanks. Sorry, it is m plus 1. Yes. Yeah, and here A is going to be OE, OL, E, EL, or C, and we are going to consider the cohomology of degree 2, and it is inner cohomology for the locally symmetric space which are defined here, and with coefficient system mu plus mu prime A and epsilon tilde prime and epsilon tilde epsilon cross epsilon prime. So why this choice of the sign? Okay, the question. So we are going to look at an isotopic component of this under the Hecke action and then induce it, and we want to interpret it as the isotopic part of the cohomology of the boundary strata, and for that to happen these signatures have to be the same. So it is either plus plus or minus minus, and it cannot be plus minus or minus plus. So that is a technical condition, because yeah, the IISER spectral sequence which Raghuram had mentioned yesterday, the base will have something more here, not just the connected component. That is the reason we have to choose that signature, and then we will be considering n cross n prime and coefficient system mu prime t twisted by minus 2 and mu t twisted by 2 a and epsilon tilde prime. Okay, and so this by Kunath isomorphism, this is actually tensor product of the cohomology group H1 and H1 of the locally symmetric space for GL2 and GL2, because that is our Levy MP here. So now we have an integral structure on these spaces as well. Okay, so that is why this makes sense. So then here is the theorem, which just comes from taking tensor product of these cohomology classes. Oh yeah, before that I have to pick another vector. So what I'll do is I'll pick, now I'll bring in the auxiliary form H. So far there it was only H prime or H double prime. So I bring in an auxiliary form H, and this is going to be in H1 of n tilde mu OL minus L to the power n. Yeah, maybe I might have to take this bar so that there is no torsion here, because this L and there is no dependence on K. L and K are not related, and then H1 streak of the same quantity over here. So we have picked an auxiliary cohomology class, and theorem that the tensor product of these two cohomology classes . double prime rho. They are congruent modulo L to the power n, but not 0 modulo L to the power n because of this choice and the theorem over there, and almost the same for this element is actually an element here in this space with OL coefficients. Okay. H prime rho tensor H, but K twisted by 2 is congruent n prime H double prime rho instead H mod of n. So now I'll present a general formalism. So we have got integral structure on the locally symmetric for GL2, space for GL2, then for the Levy, now for the induced. Okay. So okay, before that I again have to set up some notation, and then I'll talk about the formalism and then stop there because I'm running out of. So A is E, EL or C, and K of 4 n plus n prime is the Mirahoric of GL4. Okay, then we define the space I for sigma f, sigma prime f, epsilon prime A, the algebraic induction of sigma prime f, and then I also take the k of 4 n plus n prime invariance. So this is going to be a finite dimensional vector space, and then I for sigma f twisted by 2 and sigma f twisted by minus 2 prime A is going to be the algebraic induction and invariance. All right. Huh? This is an algebraic induction. So whenever in the context of automorphic forms, we throw in the modulus character for the parabolic subgroup, but here we don't do that. It's the usual induction. So it is from happening from the isotypic component of the cohomology. Okay, so from where to where? So this is an MP AF module, right? The one without the induction, and then we inflate it to the parabolic. So this is a PAF module now. Trivially, we are extending it, a trivial action we are considering on the unipotent radical, and then we are inducing it to GL4AF. So that is the induction. Okay. So So it will be all the functions from yeah GL4 AF to this quantity over here, such that f any g I can write it as I can write it as pk using this Iwasawa decomposition. Yeah, so it is, and then we further break it down via this. So what can we? It will be locally constant. Yeah, those kind of functions when we consider. Yeah, smooth. Yeah. Yeah, the A is just to emphasize the. Yeah. The, huh? Yes. Yeah. All right. Then what we do is now we collect. By the way, notice that here I am considering E, EL, or C. Okay. I still haven't defined what is for OE. So I will collect all the isotopic components and with the signature as well. Okay, these are each of these spaces, and tau f and tau prime f are varying over all the basically in the co-shriek for the weight mu prime and mu, and mu prime by 2 mu divided by 2 a is basically again these three direct sum, and tau f twisted by 2 and tau twisted by -2 epsilon prime a. All right. So now I'll present this is going to be a purely formal discussion now. Let V be an admissible MPAF module over a E or EL, and this induction this will be an admissible GL4AF module, and if I'll take now momentarily I'll take open compact subgroup of GL4AF. Then I want to know the KF invariance of the algebraic induction, and this is coming from Mackey theory. There is a Mackey isomorphism, and the direct sum is varying over all these double coset representatives. Okay, and it is given in terms of the inducing data. And this map is quite explicit. We take a phi f and then we sum it over after we evaluated psi f. Okay, and I'm going to explain what is VKF MP. So sorry, not V KFMP. So those are the invariants. KFMP Xi f is going to be uh, we conjugate KF by Xi f and then intersect with PAF and then take its projection onto the Levy quotient. And so this is a subgroup of MPAF. And say suppose we have a integral structure not V KF MP Psi f, then it's almost immediate as to how to define the integral structure here. So momentarily let me call it not this thing. So it will be all the vectors here such that if I evaluate it at Xi f, it should land here. So that will be the integral structure. So now towards that, this is the integral structure we will be giving on the induced, the KF invariance of the induced space. Now here is a technical lemma. So there exists for each divisor for all m dividing n prime, which forms a complete set of coset representatives. These are coset representatives of this space over here, which I have written down. PAF mod GL4 AF mod KF n plus n prime. The Mira-Horik now, such that Xi f m, sorry, the KF MP Xi f m, this subgroup over here turns out to be exactly the congruent subgroups of this form, or products of congruent subgroups of this form. Okay, so this lemma is quite technical, and I won't. And this is how this is what we use to give integral structures. Now this immediate. So I'll write here. Right here. So it's immediate from that lemma that what is the shape of this induced space. So I'll write it as corollary. So again, here A is one of these fields. I4 mu plus mu prime A is actually isomorphic. Running, the sum is running over all products m prime, which is equal to n prime. And here there is no induction, it's just cohomology of the locally symmetric space for the Levy. All right, this is clear from that isomorphism and the description of KF MP Xi of m. And then similarly we have sorry, this should be m cross m prime. This is m prime cross m until the okay. Now I'll just write a line. If not A is OE or OL, I'll just take a few more minutes and finish this discussion. Yeah. Okay, 3 minutes. Okay. So if then the definitions of I for mu prime mu not A, this is clear. This is clear. So what is that? So that is just going to be, we have OL, we just give OL, take A to be OL here, this is well defined, and then pull it back here, and that is what is transport the structure, and that is what going to give us the integral structure on this whole huge induced space. Right. So now with this, we can actually define two vectors, which will be at n, it will take our V naught epsilon prime. Yeah, okay, maybe using, I'll just try this. So I can pick two vectors now, phi naught prime f, coming from the cohomology classes. Oh, I erased, yeah. The tensor product of these two cohomology classes, which I was talking about, from that I can create a phi naught prime f and phi naught double prime f. These are going to be, and which will be coming from the explicit description of this coset representatives and those cohomology classes. These will be induced vectors such that they will be congruent modulo L to the power n, but they won't be 0 modulo L to the power n. And this is with respect to the lattice which I have described here. Okay, and this should be thought of as we are summing over some lattices and then give, that is the lattice structure on the induced space. So, and here is where we have to use that our cusp forms to begin with our new forms. If they are just eigenforms, this technique won't work. And similarly, we can define, so maybe I'll just tell this is in I for mu plus mu prime OL, and then there is and this is in I for OL, and they have been obtained from this, and then there is a final theorem, and I'll stop. So the effect of TIs. So I'll tell you what is TIs. I hadn't defined this, but it was there in yesterday talk. The effect of this on these special vectors, which were constructed out of this double coset representatives and the cohomology classes of the Levy. This is going to be C infinity sigma times sigma cross sigma prime dual over L on sigma cross sigma prime dual prime F, and okay. And so this was the operator which Raghuram had told yesterday. So the base change of this operator is Actually, the standard intertwining operator evaluated at -2 sigma tensor uh, sigma sigma tensor sigma prime at the level of cohomology. So that is the operator, this operator, and these classes are constructed out of some EL description of the at the level of EL or OL it is defined, but there is no reason that this should happen. But yeah, this is also somewhat technical, even though the statement is easy to see. And now our main result on the congruences is actually a formal consequence of these two properties and the properties of these two vectors. Okay, so I'll stop here.
Any questions, comments, remarks?
Yeah. Yes, yes, yeah, exactly. Yes. Yes, with L not in S ice. So S ice I didn't have time to describe. So we assume that then those become L-adic integers. Yeah, and if I further assume that they are L-adic units, then I will get on the left of the line of symmetry as well by using the functional equation. Yeah, the main theorem I had stated was on or to the right of the line of symmetry. The ratios which we are considering, the critical values, they were coming, it is not the entire critical set. It was only on or to the right of the line of symmetry. To go back to the left of the line of symmetry, if we further assume they are L-adic units, we get a statement. So with that assumption, yeah, these ratios, they become L-adic integers.
Any more questions? If not, let's answer and we will resume again in 25 minutes.
Thank you.